Hi and welcome to Vulkan from Zero to Hero.
In this section, we are going to draw our first triangle.
In this video, we are going to create pipeline. Welcome back. After creating command buffer, we need to create a pipeline. The graphics pipeline is the sequence of operations that shows pixels in the render targets. The input assembler collects the raw vertex data from the buffers you specified and may also use as an index buffer to repeat certain elements without having to duplicate the vertex data itself. The vertex shader runs for every vertex and generally applies transformations to turn vertex positions from model space to screen space. It also passes per vertex data down the pipeline. The tessellation shaders allow you to subdivide geometry based on the certain rules to increase the mesh quality. The geometry shader runs on every primitive, triangle, line, point, and can discard primitives or append more primitives. However, because of poor performance, it is not used very much. The rasterization stage discretizes the primitives into fragments. These are the pixel elements that they fill on the frame buffer. Any fragments that fall outside the screen are discarded, and the fragment shader is invoked for every fragment that survives and determines which frame buffers are written with which color and depth values. A compute shader is a shader stage that is used entirely for computing arbitrary information. While it can do rendering, it is generally used for tasks not directly related to drawing triangles and pixels. A compute shader provides high-speed general-purpose computing and takes advantage of the large numbers of parallel processors on GPU. The compute shader provides memory sharing and thread synchronization features to allow more effective pair programming methods. Input assembler, rasterization, and color branding are known as fixed function stages. These stages enable you to tweak their operations by using parameters, but their work is predefined. Other stages are programmable, which means you can upload your GLSL code to the graphics card to apply the exact operations you want. I mentioned GLSL. Actually, GLSL is a short term for the official OpenGL shading language. GLSL is similar to C language and is a high-level programming language for several parts of graphics card. The main difference is that you don't have pointers like C language in GLSL. With GLSL, you can code programs called shaders which are executed on the GPU. Let's go back to our project. We need a pipeline class. We will use this class in order to create Vulkan pipeline. First, let's create a C++ and header files for pipeline. Because in this section we want to draw primitives via GPU, let's create another header called mesh.h. We just need to define some enums and structure here. The first enum is vertex declaration. In this enum, let's declare the following enums. These values will be used for specifying types of each vertex. For example, when we say vertex position color, it means our vertex contains the following information: a 3 floats for storing position plus 4 floats for storing color. Another enum is vertex attribute. This enum should contain the following data. These are attributes that we will use for vertex in our code. For example, v underline vect3, v underline pose, and v underline route are the same because all of them are defined as array of 3 floats. Each vertex needs a binding attributes. So let's define a structure here called vertex binding attributes. We need a vertex declaration, binding attributes, and a constructor for this structure which gives vertex declaration as an input parameter. Go to the mesh.cpp and implement constructor. This constructor is responsible for setting vertex attributes based on inputted vertex declaration. Now go to the pipeline.h and let's define pipeline class. This class contains a constructor and destructor, load, bind, and release functions. For private members, we need a VK pipeline object, a VK pipeline layout, and a VK descriptor set for shader. The load function should have the following input parameters: a shared pointer to device, vertex binding attributes, primitive topology, pointer to current render path, pointer to shader, viewport and viewport Caesar. Pipeline cache name and dynamic states. Create infos for rasterization and multipass. And multi-sample states, and finally blend states and blend color. The bind function should have the following input parameters: command buffer and pipeline bind point. Make sure to add two functions, one for getting pipeline handle and another for getting pipeline layout handle. Let's go to the pipeline.cpp. After implementing constructor and destructor, let's implement load function. In this function, first we need to check whether this vertex declaration and shader are valid. Then check the shader stages. And after that, let's add 3 create info pointers. One for vertex input state create info, one for input assembly state create info, and the other for dynamic state create info. We need to store shader descriptor set here. Let's get it from shader. We should define another function called generate pipeline layout info with the following parameters. Actually, this function will be used for initializing pipeline layout create info. For implementing of this function, we should iterate over all binding attributes and find the stride. For example, for v float, v texture index, and v scale, I mean if a scale is just a float number, we just need a float value, and each float contains 4 bytes. So value of stride should plus with 4. Nice. Then we should create vertex binding description like here. Okay, now we need to calculate vertex offset based on vertex attributes. Also, we should create vertex attribute description in this stage. Alright, we need to create an instance from vk pipeline vertex input state create info. Let's initialize it like this, and we should create an instance from both vk pipeline input assembly create info and vk pipeline dynamic state create info. Finally, it's time to create an object from pipeline layout create info and return it. After we've got create info for pipeline layout, we can create it via vk create pipeline layout. Before creating pipeline, we need viewport state create info, color blend state create info, depth stencil state create info. The vk pipeline viewport state create info structure specifying parameters of a newly created pipeline viewport state. The vk pipeline color blend state create info structure specifying parameters of a newly created pipeline color blend state. And the vk pipeline depth stencil state create info structure specifying parameters of a newly created pipeline depth stencil state. Before calling vk create graphics pipeline, we should create an object from vk graphics pipeline create info structure. This structure specifies the parameters of a newly created graphics pipeline. We should set all the desired pipeline features here: the vertex input state, the input assembly state, dynamic state, tessellation, rasterization state, multi-sample state, depth stencil state, color blend state, viewport state, and the layout of pipeline which must be created. Also, we should pass handler of render path to this structure. Now call vk create graphics pipeline function and make sure to check the returned result of this function. We need another function in order to bind to the pipeline, which is responsible to call vk command bind pipeline. And finally, release all resources in release function. We should add two public functions in order to get the pipeline handle and pipeline layout handle from outside of this class. Now it's time to define two instances of shader and pipeline in our scene class. In the next video, we are going to create shader.